Okay, it's okay.
It's okay right now?
Yeah.
Yeah. Good morning to everyone. Our project is battery powered DC to DC buck boost converter with two controlling methods and single dashboard interface. In this project, we designed a buck boost converter, analyzes its behavior, and compare two different control methods using Matlab Simulink. Coming to buck boost converter. Okay, a DC to DC converter changes one DC voltage level to the another. There are three main types. One is buck converter, second one is boost converter, third is buck boost converter. Coming to the buck converter, it reduces the voltage so that output is lower than the input. So boost converter, it increases the voltage so that output is higher than the input. Coming to the buck boost converter, it can do both. It can produce an output voltage that is either higher or lower than the input. Because of this flexibility, buck boost converters are widely used in battery powered devices and power electronic systems. Coming to the literature review, from the literature, we found several important points. First thing, buck boost converters are commonly used in battery systems and renewable energy systems, where the voltage can vary. Second, the inverting buck boost topology is popularly because it uses only a few components. One is MOSFET, one is diode, and one inductor and one capacitor. Third, the operating the converter in continuous conduction mode is preferred because it reduces the current ripples and improves stability. Finally, control of the conductor is challenging because of nonlinear behavior. So the controllers like PI controller and cascade controllers are often used. Coming to the project overview, this slide shows the main specifications of our project. The input voltage is 10 volts and the output voltage ranges from 5 volts to 20 volts. Coming to the load resistance, it is 10 ohms and the switching frequency is 20 kilohertz and it allows the voltage ripple is within 5%. The conductor operates in the continuous conduction mode. Our main object was design a buck boost conductor that works across 5 to 20 voltage range, implemented two control methods like PI controller and cascade controller. And here, in and coming to the slide 5, it's circuit topology. This slide shows the inverting buck boost converter. The main components are MOSFET, inductor, diode, capacitor, load resistance. Coming to the MOSFET switch, connect the input to the inductor, whereas inductor stores energy when the switch is on and releases it when the switch is off. Coming to the diode, provides a path for current when the switch turns off. Capacitor filters the output and reduces the voltage ripples. Load resistance represents the connected load. In this topology, the output voltage is negative with respect to the input ground, which is why it is called as inverting buck boost converter. And here, let's compare the inductor sizing and capacitor sizing. Okay, the main calculations value for the inductor and capacitors are the minimum calculator inductor were 185 microhertz. We selected the large value of 2.2 millihertz to improve the stability and to ensure the CCM operation. For the capacitor, the minimum value is 66.7 microfarads. We selected 34 microfarads to reduce the output ripples and improves the performance. These component values helps to maintain the stable operations and low ripple in the conductor. Here, this shows the main equations used in this design. The voltage converter ratio shows the relation between the output voltage, input voltage, and duty cycle. The duty cycle equation tells us how long the switch must stay on to achieve the desired output voltage. We also calculate the average inductor current, which helps us to design the inductor and to ensure the continuous conducting mode. These equations were used to determine the operating points and to design the control systems.
Hi everyone. I'll be covering our first control method, the PI voltage controller. The PI controller is a standard feedback loop. The output of the controller becomes a duty circle command, and we limit it between 0.05 and 0.95 to protect the converter. For tuning, we went through 4 steps. First, we set the target crossover frequency at 25 radians per second. Second, we calculated an initial KP of around 0.026. Third, we placed the integral 0 to get an initial KI of 0.065. And fourth, we ran simulations and fine-tuned the values. The final parameters are Kp equals 0.005 and Ki equals 0.15. Next slide. Here's the simulating model for this controller. You can see the PI block, the duty circle limiter, and the feedback path all connected to the PWM generator running at 20 kHz. Because our converter produces a negative output voltage, we handle the polarity by reversing the voltmeter connections directly in the circuit. Next slide. Now you can see the results. First is a step-down case where Vref equals 5 volts. The performance is very strong here. Overshoot is just 0.1%. Settling time is 0.2 seconds. And steady state ripple is 3.5%. Well within the 5% requirement. The operating point past the specification. Next. For the step case at 20 volts, the results are also good. Overshoot is 2.0%. Settling time is 0.5 seconds. And steady state ripple is 3.7%. Still within the 5% limit. The operating point also passed. Both keys meet the repo specification, which confirms that the PI controller works correctly across the full operating range. This completes the PI controller section. My teammate will now present the cascade controller.
Hello everyone, I'm Pratami. Cascade controller is built in Matlab Simulink. First of all, as you can see on the screen, the inner loop is fast. It directly controls the inductor current by adjusting the duty cycle in real time. The outer loop is slower. It reads the output voltage, compares it to the reference, and tells the inner loop what current level to target. A key feature here in the saturation block. Go to the next slide. This is our cascaded control built in Matlab Simulink. The key feature here is the saturation block, which automatically enforces a hard current limit of 6.9 amps, giving us built-in overcurrent protection. This is the main advantage of the cascade control method. Next slide, please. In test case 3, step up to 5 volt. The cascaded control achieved only 2% overshoot and 2.3% steady state ripple, both well within the 5% specification, and the settling time was 1.2 seconds, which is slower than the PI controller by 0.5 seconds. This is an expected trade-off, and the inner current loop deliberately limits how aggressively the converter responds at the low current levels. But this result is notably clearer and smoother transient specification. Next slide, please. Test case 4. In test case 4, also the result of the whole project, the step-up case of 12 volts. The cascaded controller achieved only 3.8 overshoot and 1% steady state ripple. It is very smoother curve. You can see that is a 6 times improvement over the PI controller at the exact same operating point. Why? Why? Let's discuss why this was happened. Because the inner current loop actually damps the LC resonance. Our LC filter has a quality factor of 19.7, meaning it is highly underdamped, and naturally tends to oscillate. The cascaded controller suppresses this directly by regulating the inductor current, while the single loop PI controller could not. Settling time was 1.3 seconds. Next slide, please. We also verified that the converter operates in continuous conduction mode at both points. Continuous conduction mode means the inductor current never drops to zero during switching. This is required by our design specification. At 20 volts, the minimum inductor current was close to 6 amps, strictly above zero. Next slide, please. Full performance. If we compare full performance, here is the complete comparison across all 4 test cases. Looking at the table, the PI controller performs strongly at 5 volts, just 0.1% overshoot, 0.2 second settling time, and 3.5 ripple. At 20 volts with the updated turning, the PI controller also passed 2% overshoot and 3.7% ripple. The cascaded controller performed consistently well across both operation points, most impressively at 20 volts with under 1% ripple. A 6 times improvement importantly. All 4 test cases passed the 5% ripple specification for both controllers. Next slide, please. Conclusion. As a conclusion, here is the project achieved. First, we designed the size the converter 2.2 millihenry and 34 millifarad, confirming continuous conduction mode with the minimum inductor current close to 6 amps, verified both analytically and in simulation. Secondly, the PI controller delivered solid performance at both operating points. Both within this specification limits. Third, the cascaded controller with further achieving under 1% ripple at 20 volts. It is a major highlight. The inner loops achieve LC damping, resolve the further fundamental resonance challenge. And fourth, the cascaded controller also provide inherent overcurrent protection, automatically enforcing a 6.9 amp current limit through the saturation band. No additional hardware required. The bottom line, the cascaded controller is a superior choice for wide output voltage range applications. Thank you.